First thing, just want to remind you that our the midterm is going to come on Monday. Okay, it's going to be only about maybe 50 to 55 minutes or so to be held, at the second half of the class. And as before, it will be mostly on sort of conceptual questions, asking you how to define certain things, examples, and so on, and a little bit on maybe some not so complicated calculations. Okay, so that's going to be that. Yeah. Hey.
Do you know when Professor Small is right after this?
Professor Small? I just saw him leave the room. I don't know where he is now. Check his office. Yeah. He should be back in his office pretty soon. He just left the room a few minutes ago. So, and it's going to be a closed book exam also, because like last time, because I'm asking you for definitions and explanations and so on. Okay. So that's that, and bring your own papers to put your answers on. So we're only left with about like 2 weeks, and so I do want to spend the rest of the time on topics in differential geometry that are relevant to physics applications. And I just sent out the rest of the lecture notes for you. Actually, it includes 4 chapters from my classical mechanics book. Most of you have my classical mechanics book already, so it's kind of a little redundant, but I realize maybe Ryan, you don't have it, and David, you said you'd check it out, but I sent it out anyway. So those will be the rest of the notes, 4 chapters, which actually has some overlappings with chapter 41 of the quantum mechanics excerpts that I sent to you also, okay? So chapter 41, which I'm about to cover, from the quantum mechanics text, is kind of like a very sort of a compactified review of some aspects of differential geometry that are relevant in quantum mechanics, but by extension be relevant in all of physics, okay? Whereas the chapters in the classical mechanics that I sent out to you has developments of those topics in a little bit more detail, but perhaps not with as many applications as in the quantum mechanics book, okay? So just to realize that there are some overlappings. And so that's it. I've sent out all the lecture notes for you. And so the rest of it will be dealing with this chapter 41 in the quantum mechanics text excerpts, and then the rest of the stuff from the classical mechanics text, which basically, the only thing really new in there is the more detailed treatment of the Riemann curvature tensor, okay, with respect to Riemannian geometry. So let me begin today by kind of talking about what we went through last time as a further lead in to some of these more general developments. We gave 2 examples of the importance of the notion of gauge fields, or AKA connections in mathematics, and by extension the notion of force fields, AKA curvatures in mathematics, okay? So the 2 examples that we studied so far were the Aharonov-Bohm effect in non-relativistic quantum mechanics, and then the magnetic monopole, both of which actually point to the use of the same group of concepts. So let's recall what happened when we talk about the magnetic monopole. We saw that if the magnetic monopole has a magnetic charge m, that's the equivalent of the electric charge, then the following quantity has to be an integer. Has to be some integer, okay? Positive integer, in fact. So m is magnetic charge, E is the electron charge. The other 2, h bar and c, are of course fundamental constants. And the importance lies in the emergence of an integer in this case. I mentioned already that in mathematics this is called the first Chern number. And in physics, it's called a topological quantum number. And we actually, by the discussion of this, explicitly constructing the magnetic field coming from a magnetic monopole, and we try to see how to relate the magnetic flux to the vector potential leading to that particular magnetic field and so on, doing the line integral using Stokes' theorem related to the flux integral, and so coming up with the conclusion that regardless of what that vector potential looks like, you have the emergence of an integer. Okay?
Yes, I'm kind of confused by what you wrote there. It says that 2em over h bar c is an element of the integers. Is that the 2em over h bar c the Chern number? Because
The whole thing is a Chern number. The integer is the Chern number.
okay, so not the set of all integers is not the Chern.
No, it is a particular integer. So it belongs to the set of, I should say positive integers in this case. Right, non-zero, okay, positive integers. So, okay, so now let me just try to do a quick rundown on how this kind of integers emerge from a mathematical context rather from the context of this special. Actually, I have to go back to the context of this special situation also because we are talking about the Maxwell's electrodynamics, okay? And so, so in the case of a magnetic monopole, what we are talking about is a base manifold that is a sphere, S2. And then I think what we were talking about is the case of fiber space, where the fiber space is the one-dimensional complex manifold, so that the gauge group, so to speak, is the group U1. Okay, gauge group is the group U1, because U1 is the group of transformations which transforms among the different basis vectors, unit basis vectors in the complex plane. Okay, and we have defined this thing called a connection one form, where A1, A2, A3 are the three components of the vector potential and electrodynamics. And actually, in this case, there are only two x's because the base manifold is S2. Okay, so K goes from 1 to 2, and then this is a one form, so we can imagine doing a two form, which is the exterior derivative of this omega in here. Okay. Now let me point out in advance that if you do something like that, this is called a curvature corresponding to a particular connection. Okay. But here, because the fiber space is one-dimensional, and these are differential one forms, so therefore it's anti-symmetric, so that goes away. Okay. In the general case, those are not just one forms, but that includes a matrix multiplication also. So it's not necessarily zero when the fiber space is multidimensional. The second term is only one-dimensional when the fiber space is. The second term only vanishes when the fiber space is one-dimensional.
I'm sorry, rewrote that. That's first Chern number, right?
Yeah, that's called a first Chern number. Right. Chern is the name of a mathematician. So now, so in this case, we have this thing in here, and then you can see that actually I'm going to define. At first I wrote this as script A. Script A in general, so you have something like that. And then I also wrote script A in terms of the actual A, which are the components of the vector potential, but then I have to stick in minus IE over H bar C like this. This is so that this thing being a Lie algebra valued form has to be anti-Hermitian, and this thing is required to be Hermitian, so I need to have something that's proportional to I, so that the Hermitian conjugate is equal to the negative of itself. Okay, so that makes it anti-Hermitian. Just like that in the rotation group case, the Lie algebra has to be anti-symmetric. In the complex vector space case, it has to be anti-Hermitian. Okay? And so you can simply perform a exterior derivative of this and get minus IE over H bar C. You introduce another summation index, it becomes dxj, which with dxk, like that. And you can then write this in a slightly different form, diaj minus djai. Then this is dxi, which dxj, but then there's a requirement that I has to be less than j, okay? Otherwise, if you make the sum unrestricted, then you have to introduce a 1/2 factor in here, which we have also done. Whichever way you want to write it, you have to be careful about it, okay? Okay. So this is mathematically what's called a curvature, but in this particular physics context, it turns out to have something that looks like the field tensor, okay? diaj minus djai is like fij, okay? It's an anti-symmetric tensor like that. Now this thing is actually a tensor because it transforms like a tensor. Omega itself is a two form, okay? There's two of these guys in here, wedged together or multiplied together. And then this is a tensorial quantity by itself with particular values of I and j. It's an anti-symmetric as clearly seen. Aij, Fij, if you call the whole thing Fij, Fij is clearly equal to minus Fji because of this minus sign in here, okay? And now the idea is this, that whereas the gauge transformation itself goes like this, in the general case of multi-dimensional fiber spaces, this is a general gauge transformation equation, which is clearly not tensorial because of the presence of this term in here. If it were tensorial, it would have to be just like that, without that first term. Because a tensor object, a transformation of a tensor always transforms a zero tensor to a zero tensor, okay? So if something is originally 0, then this term goes away, but then in general you still have this thing in here. So that under the gauge transformation, this omega can go from 0 to non-zero and vice versa, okay? So that is the main reason why that is not considered as a tensorial object. But then you can ask the same thing about this quantity in here, whether this quantity is a tensorial object or not, and the answer is that it is. And the answer is that it is. Why? Because we can prove this very easily, in fact, although I won't do it right now, I may do it a little bit later, that omega itself under this gauge transformation that is brought about by this transformation matrix G, okay? Under the gauge transformation using G, then you see that omega prime is in fact equal to G omega G inverse. So that makes omega tensorial, okay? You see the difference between these two transformation rules? In the one case, there's this funny thing going on. That's why this is called a local gauge transformation, because the G itself depends on the position in the underlying space. So G is actually a function of X, okay? So that it makes sense to talk about the differential of G. If G were constant all over the place, then dG would be equal to 0. If G were constant all over the place, that would make it what is called in physics a global gauge transformation. Yeah.
Is G an element of U1?
In this case, in this simple case, it is. But I'm going back to the more general case where you have EI prime is equal to GIJ EJ. Then, of course, G would have to be whatever it is, okay? It's just a transformation of the basis vectors of the fiber space. So in this case, the fiber space is a one-dimensional thing, so it is U1, okay? But you see, the element in U1 depends on where you are on the underlying space. So that's why it's called a local gauge transformation. One of the most important things in physics theories is that it's required to have local gauge invariance. In other words, you see, what is a local gauge? A local gauge is just a local pick of the frame field, right? So if you go to another frame field, then you have locally changed a gauge because these guys depend on position, okay? These guys depend on position. In other words, in general, you have something like this. The transformation depends on the position, okay? The x's are just the local coordinates of the base manifold, all right? So if you undergo a local change of gauge, both of these guys will change. The connection will change, so will the curvature. But there's something which is required to be unchanged, and in the case of physics theories, it's called a Lagrangian, okay? In the case of quantum field theories. The Lagrangian has to be gauge invariant, so to speak. In general, we mean this to be a locally gauge invariant Lagrangian. And then as a result, then the Euler-Lagrange equations, which result from that Lagrangian, will be invariant in form also. Those are the equations of motion, and so therefore the physics of whatever you are studying does not depend on the gauge. In other words, it does not depend on the local pick of a frame for the description of your physical phenomena. Okay? So when you state it in those terms, it appears to be quite trivial. The physics does not depend on local pick of frames. But when you state it in mathematical terms, it becomes all this stuff about gauge, gauge transformations and so on and so forth. Okay, I'll certainly have occasion to go over this in some more detail in this last couple of weeks. But right now, let me just proceed. Now, this is called a curvature, okay? It's called a curvature. And in particular, we'll see that from this formula in here, this is a very formula, we'll be able to obtain the formula for the Riemann curvature tensor in the case of Riemannian geometry, and also the Yang-Mills potential in the case of non-abelian gauge theories and so on and so forth. Remember the first handout that I gave you in the beginning of this course, okay? Showing two formulas, one for the Riemann curvature formula which appeared first in physics in Einstein's paper in about 1915, 1916. The other one was a formula for the non-abelian gauge field, which first appeared in 1954 paper by Yang and Mills. And so that's why henceforth these types of gauge field theories are also known as Yang-Mills theories. But then, much of the purpose of this course is to try to show you that both of those formulas which have very different physical applications are apparently mathematically the same thing, okay? Both of those are curvatures of some sort. But then you have to think about not just the curvature of a particular Riemannian space, but curvature of a general vector bundle, or even more abstractly, what is called a principal bundle, which we'll talk about a little bit later, okay? The curvature comes from a connection. So obviously the connection, the omega is the more basic thing, right? Because it's out of the connection that the curvature is defined, okay? So if this thing is 0, then the curvature is 0, but this is only a local formula, okay? You can have 0 curvatures somewhere, but non-zero curvatures elsewhere in a manifold, okay? But if you can show that it's everywhere 0, then of course, then the whole thing is 0 curvature, okay? Such as three-dimensional Euclidean space, okay? Now, because of the fact that the curvature itself, under a certain gauge transformation, transforms like a tensor, then I guess the mathematician would try to kind of generalize this to try to think of what else would be invariant under similarity transformations also, okay? That's based on the curvature itself. Well, I don't know how Chern came up with this, but he wrote down this formula. He said motivated by this in here. Then he's led to consider this quantity. Here's a two form in here, and it can be thought of as a matrix, okay, because it's a two index thing in here. And so this is a matrix, okay? The one itself obviously is an identity matrix, okay? And the I is thrown in here because of the requirement of this, of dealing with complex vector bundles and so on and so forth. And he's trying to see, now this itself is obviously not invariant because omega changes to something else, okay? But since there's some functions of this omega which is invariant, okay? When you think of matrix algebra, when you think of a matrix, some things are invariant under similarity. Many things, as a matter of fact, are invariant under transformations, right? Among which is the trace, for example, is invariant, and there are a bunch of other things also. But then there's also something called a determinant of the matrix, which is invariant under a gauge transformation also, okay? And so he was motivated to consider this thing in here, okay, the determinant of that. And now, omega itself is a two-form. Omega itself is a two-form. But you know, when you calculate each element in this omega matrix is a two-form, okay? The omega is a matrix. What is the size of the matrix? The size of the matrix depends on the size of the fiber space, okay? So if your fiber space is three-dimensional, then each of these guys is a two-form, like that, okay? But when you calculate matrices, you have products of these things, right? You have products of these things. So, but then, you know, each term in the product would be a 2n form or 2j form, right? Because this thing itself is already a 2 form. So you multiply some of these things together. Each thing that appears in the expansion would be a 2j form. And so he wrote this as something like this, 1 plus C1 omega, each depends on omega, plus C2 and so on and so forth, plus up to a maximum number, like that. This thing in here is the, okay, where you take some general one of this, it's called a Cj omega. This is actually a 2j form. Okay, because omega itself is already a 2 form. And so he kind of just wrote, so each term in here must be an even number form. Okay, because you're multiplying these things together. Each is a 2 form. So multiplying these things together, each one must be an even order form, so to speak. So each of this is a, Cj is a 2j form, a differential form. So you see that when you deal with differential geometric studies, the technique of differential forms is really very important. And I think I have introduced you to some elements of it. And in chapter 41 of the quantum mechanics text, there's a kind of a very fast-paced sort of compactified sort of elementary introduction to the subject, which we did kind of in our classical mechanics class also, you remember. But I guess I will take some time to sort of develop this a little bit more in detail, and that's given in one of the chapters in the classical mechanics book that I just sent out to you. Okay? Okay. Now, suppose that, you know, the dimension of the underlying base space is n. So let's say the base space is m, and suppose dimension, I'm talking about a general case now, right? You know that a differential form on this base space, if it's a 1 form, it consists of superpositions of this, okay? If it's a 2 form, it consists of superpositions of this, okay? If it's a 3 form, it consists of superpositions of something like that, and so on and so forth, okay? Now let me ask you a question. If I'm dealing with a base space whose dimension is 3, what is the value of a 4 form? 0. Why? Because you only have 3 independent x's, right? So whatever the fourth thing you put down here has to repeat one of the earlier ones, no matter what it is, okay, when you sum it over. So there's a top form, so to speak. Top form simply refers to the highest order form on a differentiable manifold. And if the dimension of the manifold is n, then the order of the top form must be n also. In other words, there cannot be a differential, it cannot be a non-zero differential form whose order is higher than the dimension of the base manifold. I hope that's quite obvious, okay? And so obviously then, that being the case, that sequence must stop someplace, okay? Because the order of these forms increases from term to term. Here's a 2 form, here's a 4 form, here's a 2q form, okay? And so in order for this to be non-zero, 2q must be less than or equal to n, right? N being the dimension of the underlying manifold, okay? And, or in other words, n must be bigger than 2q, okay? Whichever way you think about it. The important thing is that the series terminates, has to terminate, okay? At least when you're dealing with finite dimensional base bases, which we usually deal with, okay? The sequence must terminate. Okay, let's come back to this very specific case when the dimension of the underlying manifold is 2 for the case of a 2-sphere. Then where does the sequence terminate?
1 second. It must terminate. There's no infinite dimensional manifold? Or am I-
We are not considering infinite dimensional manifolds. We're only considering finite dimensional manifolds. Okay? Yeah.
Okay, another question.
Yeah.
When you calculate the determinant of whatever connection matrix you have,
Yeah.
are you doing it by considering the product as the exterior product?
Exterior product, yeah.
So, calculate the determinant of the finite matrix, you need to take this.
So this is a you just use the ordinary rules of evaluation of a determinant, but then the products would have to be exterior products. Yeah, yeah, that's a situation, okay? Okay, coming back to sort of a very specific example, in this magnetic monopole example where the base is S2, so obviously the dimension of the underlying manifold is 2, so where does the sequence terminate? The first one, the first one, okay? Because first one already would involve a 2 form, and the 2 form is a top form in this case. So all these guys go away after the first one, okay? But in a higher dimensional manifold, then you would have some of these other guys also, okay? Okay, here comes a little bit more mathematics. Now, this is the result of a theorem, which is quite a deep theorem, which I cannot prove to you. It's quite difficult to prove. It's called the Chern-Weil theorem. Says that for all the j's in this expansion, the exterior derivative of this 2j form must be equal to 0. It just turns out to be that case. Okay. So that means the form is a closed form. The form is a closed form. If the form is a closed form, then you ask the question whether it's also exact. Normally, a closed form is not necessarily exact. Now, what is meant by exact? An exact form is one which can always be expressed as the derivative of as the exterior derivative of a lower order form. Okay. So, in other words, if a form omega is exact, then omega must be expressible as d of something else, a lower order form. This is called exact. Exact forms are very nice because you can integrate them. Okay. The integral is just omega prime itself, okay? Okay, so you have the situation that exact forms are always closed, but closed forms are not necessarily exact. Okay. Why is an exact form always closed? Because an exact form can always be written as something like that. And if you d that must be equal to 0, because in general d squared acting on anything must be equal to 0. Okay. So now buried within these simple statements is something that needs to be developed in more detail. But these are nice results to know and to use. Okay. D squared is always equal to 0. I'll show you a little bit later. So a closed form is, an exact form is always closed, but a closed form is not always exact. But then among the closed forms, there may be a subgroup or something which is exact. So you can, and in fact you can show that to be a normal subgroup. So you can form what's called the quotient group of the closed forms divided by the exact forms. Okay? That's called a cohomology group. Okay? So you have the group of closed forms. You showed easily that it forms a group. Okay? Closed forms over the subgroup of exact forms. Quotient in the sense of group theory. Let's say closed forms of order n, okay, of order n. Then this is called the H upper index is called a cohomology group. Okay. It turns out that cohomology groups, just like homology groups, they are due to each other. They are topological properties of the underlying manifold. It does not depend on the particular connection, does not depend on the curvature and so on. They are totally topological. Okay? All these things, homotopy groups, homology groups, cohomology groups, are all carry topological information on the underlying manifold. And when people study abstract manifolds and try to investigate the topological properties, they use these algebraic methods, such as calculating the cohomology groups or the homology groups or the homotopy groups, and higher, these groups of different orders and so on and so forth. And all this yield fairly rich topological information on the underlying manifold. The interesting thing is that homology groups has to do with loops that can be deformed into each other, whereas cohomology groups has to deal with differential quantities, has to deal with these analytical things, the differentials and so on and so forth. But the wonderful thing is that it can be shown that they are dual to each other. So as vectors, at the same time, these can be considered as vector spaces also, other than the group, okay? And so you have the thing which is dual to that, we call that lower n, which is called a nth homology group, and the H upper n is called the nth cohomology group. And it's the substance, is the content of the theorem that these two things are dual to each other as vector spaces, which is quite a useful theorem also, okay? So the main thing is that you can get topological information by studying differential objects on the space. That's called differential topology, okay? And so this business kind of hooks up with a lot of interesting fundamental areas in mathematics. So coming back to this thing in here, so this is a closed form. This is a closed form because that's what it says. D of that Cj is a closed form because d of that is equal to 0. That follows from this theorem in here. So as a result, the Cj itself defines what is called a cohomology class. Okay, the cohomology class are just the elements in this quotient group in here. Okay, so it defines a cohomology class. And these are what are called the Chern classes in differential geometry. Those things, the Cj's, are what are called the Chern classes. There are many other kinds of so-called classes, such as the Euler classes and the Pontryagin classes and so on and so forth. Those things that people come across in the study of differential topology. But the Chern classes are the classes which are important in the study of vector bundles which have complex vector spaces as fibers. That's why the appearance of the factor I over there. And of course, that's the one that's useful in quantum mechanics, because in quantum mechanics, we do deal with these complex bundles, so to speak. Okay, complex bundle simply means that the fiber spaces are complex vector spaces. Can be one-dimensional, can be two-dimensional, can be any dimensional, as a matter of fact. Okay, so when you deal with such complex bundles, the geometrical objects that emerge as the objects of importance are then the Chern classes. And this is one of the reasons for the importance of differential geometry in quantum mechanics. Okay. All right. Now, so CJ then being these Chern classes is an element of what's called the 2J, the cohomology class, cohomology group. Okay. Sometimes called cohomology class. Cohomology class. The 2J cohomology class. Independent of the connection, because that's a topological element. Even though they are calculated from a connection, because the omega is calculated from a particular connection. Because the omega is calculated from a particular connection. By the time you evaluate these classes, it's the same class. It follows, different things coming from different connections and so on comes into the same class. So it defines something that is independent, quite independent of the connection or even the differential structure that's inherent within the manifold. And so it's a topological object in here. Now, then these are forms of certain orders, right? You take a CJ, it's a 2J form. And so you can imagine integrating a certain 2J form over a J-dimensional, over a 2J-dimensional submanifold of the original manifold that is without boundary. Okay, all right. A form. What are forms used for? I mean, what are they good for? They're good for integrating over. Okay, it's like a differential object, and you integrate over some. So you integrate a one form over a line. That's a line integral. You integrate two form over an area. That's an area integral. You integrate a three form over a three-dimensional subregion, and so on and so forth. Okay. In this case, we're only dealing with even dimensional forms. And so you need to integrate them over, if you want to do any integration, whatever, you need to integrate them over even dimensional subregions. And it turns out that if you integrate over subregions that are without boundary, those are called cycles in mathematics, then the result always turns out to be an integer. That's a deep theorem. Okay? That's a wonderful thing about it. Okay? So those are the result of the integration is called a Chern number. The integral of a Chern class over some submanifold is called a Chern number. It always turns out to be an integral. And, an integer, okay? And so, integer. And so this has to reveal something that is deep within the topology of the underlying manifold that we are studying, okay? That's why the importance. So they're the so-called, well, apparently the first Chern number is the integral of the first Chern class. It's the integral of this thing, which as we saw is just like the curvature, okay? And so the second Chern number is the integral of this thing over some closed, over some two-dimensional, four-dimensional region, subregion without boundary, and so on and so forth, okay? Okay. So that's the whole nexus of of these ideas and concepts, which make them very useful in physics. I've of course skipped over an immense amount of detail Not to speak of the proofs of these theorems and so on and so forth. By the way, let me indicate very quickly to you also the relationship. We have defined the so-called cohomology classes, and what are the homology classes? The homology classes have to deal with loops, okay? Loops without boundaries are called cycles. Not necessarily loops, but higher dimensional subregions which are without boundary are called cycles, okay? Usually if there's a subregion, M, for example, when that region is without boundary, we write it like that. The partial sign is sometimes used in topological considerations to mean the boundary of a certain region, okay? And, okay, so let me, and then, now, within those cycles that are regions without boundaries, there may be certain ones of them which are the boundaries of something else, okay? Those are called boundaries, okay? Since they are the boundaries of something else. So this forms a normal subgroup of this thing in here, so you can think of the quotient group of those two things. That one is called the nth homology class. If this cycle is an n-dimensional subregion, okay? And so among those, there are those which are boundaries of an n-1 dimensional subregion, for example, okay? So the mathematical theorem is that, it's called a de Rham theorem, by the way. I don't know if you've heard of that. Is that these two groups are exactly isomorphic to each other. It's called a de Rham theorem, yeah.
So this is the quotient group of the group of cycles and the normal subgroup of
boundaries, the cycles which are the boundaries of something else, yeah.
Combine cycles to form another cycle.
Yeah, you can.
But how?
So I give you an example. So if you have one cycle like that, these are going in opposite directions. So one minus the other is the boundary of the annulus, for example, okay? Similarly, you can think of, now this is a good point actually, you can combine them simply by multiplying a cycle to be thought of as a vector by some either real number or complex number, okay? So you may have 2c1 minus 3c2, for example. You loop around this 2 times minus this loop around 3 times and so on, and you get another cycle, okay? And so on and so forth. And similarly, you can group together the boundaries also, the ones which happen to be a boundary of something. So for example, if I go to the torus, okay, this loop in here is apparently a cycle because it doesn't have any boundaries, okay? Right? Now, if you think of this loop in here, it's also a cycle because that doesn't have any boundaries either, okay? So you think of another one like that, that's another cycle. Now, just as in this case, I can think of this one minus this one. Then this one minus that one becomes the boundary of this strip in between. Okay? Like that. Okay? So this one is a boundary of something that's one dimension higher. Okay? So these two can be thought of as within the same class, right? Because, you know, one minus the other becomes the boundary of something. So one minus the other in here becomes something in here. So this guy is the normal subgroup of this. You can show that it's a normal subgroup, okay? And so you have the cycles over boundaries as what is called a homology group that's defined in terms of these cycles and so on. The wonderful thing is that, you know, that's completely isomorphic. It has a vector space structure, and also it's a group to the cohomology groups. It's called the de Rham theorem. Okay, yeah.
I'm just a little confused. When you go down to the 8 subscript n, and
Oh, if this is something in a dual, then something that is the dual of that is, you write it as one is upper and one is lower and so on. Just like we write the ordinary indices, x upper I and x super I. One is considered as components in the dual space of the other one because they transform oppositely, inversely, and so on. Okay? Now, admittedly, all this is rather new, rather unfamiliar, and rather abstract on top of that. But the point is that they all connect together in some essential way, and it so happens that they all have a lot to do with physics, okay, believe it or not. Okay, so let's immediately come back to the physics. Let's calculate the first Chern class in here, okay? So we calculate this is the omega, right? So we calculate this, and you'll see what we mean. So C1, the first Chern number, small c. Small c1, I wrote down Chern numbers. Anyway, let's go back here. This is omega. And so little c1 is the integral over the base manifold. The entire base manifold is a manifold without boundaries. The sphere itself doesn't have any boundaries, okay? Of C1 omega in here. The C1 omega is just omega, as we saw. So this is just omega. Omega here is considered as a two form like that, okay? And this is called a first Chern number, according to our mathematical definition. It's number 1 in here, called the first Chern number, okay? And we write down exactly what it is, including all those funny factors. One has to, C1 in here is not just omega, but in fact it's equal to I over 2 pi times omega. This is important, okay? C1 is I over 2 pi times omega. Those factors have to be in there in order to make things work, okay? And now we write omega in terms of the other things. So it's I over 2 pi multiplied by minus IE over h bar c this whole thing is just dA. Omega is dA, all right? Because this thing is, this is A in here, so omega, wedge omega is equal to 0. So this is dA. The two components of the vector potential in this case, integrated over the sphere. Now, we did the calculation already last time, actually, right? We saw that by using Stokes' theorem, dA integrated over the whole sphere is like A integrated over the boundary, okay, by Stokes' theorem. You just peel off this here. Actually, what we did was this. The whole sphere is like that. We split that up into 2 parts, okay? So this is actually the sum of these 2 integrals over these 2 regions in here. And we saw that we have to, at the boundary, we have to do a gauge transformation. Remember that our discussion last time? And then by using the Stokes' theorem, you reduce each of these area integrals, which this is, to a line integral, okay? You reduce the area integral to a line integral over each part. And in the top part, we use, A itself is simply written as AJ dxj here, okay? And so we saw that this is equal to, well, first let's take care of these factors first. I times I is minus 1 kills this minus 1 in here. So you have E over 2 pi h bar c. This becomes a sum of 2 line integrals, the northern hemisphere one minus the southern hemisphere one. The minus sign in here because you have to go around the boundary in opposite directions, okay? dotted with dl. The dl, let's say, is chosen to go in this direction, so you have a positive sign associated with a northern function for A and a minus sign associated with a southern function. But by gauge transformation, we saw that this has to be exactly equal to 4 pi m, the flux integral of the magnetic field. Okay? Well, actually, we knew that already from the beginning because dA is actually equal to the magnetic field. Okay?
What is that symbol on top of 2 pi h bar c?
Which one?
The symbol right there above the 2 pi h bar c. Yeah.
Sorry, E. Electric charge. Electric charge in here. Electrons charge. The electron's electric charge. Okay? So this is equal to 2 pi over h bar c, and the flux integral is simply 4 pi m for a magnetic monopole. And since this is C1, it has to be an integer, so the whole thing has to be an integer, right? So the whole thing has to be an integer, and so it works out to have the result that I stated over here. The whole thing has to be a positive integer, like that. Okay? Cannot be 0. Has to be an integer, positive integer. Everything is positive. Okay? Actually, can be a negative integer if we choose a negative sign for the electron's charge. Okay? So you see how the integers emerge quite independently of all the physics. It emerges as a result of the study of certain topological classes on the manifold, so-called cohomology classes. It just so happens that this integral that we are dealing with in here is the integral of the curvature, that's all. It's almost by accident, okay? And you see this kind of result then can be extended or generalized in many different directions to many different models which are applicable to physics, such as topological solitons, or you find people studying these things in physics. Okay, all kinds of weird things, topological constructs in condensed matter theory, and so on and so forth. Okay, you have a topological quantity that's classifying all those different kinds of pseudo particles in all kinds of physics applications. A large class of them happens to be within condensed matter physics. Okay, certain kinds of lattice structures having very funny kinds of topology, two-dimensional physics in the Hall effect having certain kinds of topology, and so on and so forth. In fact, the fact that the integer quantum Hall effect is precisely something like this. There's something called the integer quantum Hall effect. When you study planar charge systems, okay, the integer comes from the fact that you have a topological quantum number buried somewhere. In other words, you have a Chern number buried somewhere in the description of, mathematical description of a particular physics problem. Okay? So now there's a whole lot of things in here to stomach and digest. I, of course, don't expect you to be able to feel comfortable with it all. This is just a quick, just based on the simplest example that we have discussed, the magnetic monopole example, just to demonstrate to you some of the relevance of some of these mathematical constructs. So now I want to go back and actually patch up some of the holes, so to speak, okay? We are going to talk about differential forms in some more detail. And before we do that, we have to understand a little bit more analytically about the notion of a tangent space, and also the notion of a cotangent space, and then tangent bundles and cotangent bundles, and so on and so forth. And from that, we can then understand the general notion of differential forms. And from that, we learn how to do exterior differentiation on differential forms, and then how to do integrals of differential forms, and understand how the Stokes theorem can be formulated in terms of those general integrals. And then once we have differential forms, then we can imagine carrying out exterior derivatives of those forms, and that's where the curvature comes in. You see, a curvature is expressed in terms of the derivative, or the exterior derivative of the connection form, which is a one form. When you exteriorly differentiate anything once, you increase the order of the form by 1. So if you exteriorly differentiate one form omega, then the result is a two form. And so this term, this term has to be a two form also, right? Because it doesn't make any sense to add a two form to a one form. You can add it, you can think in terms of a direct sum vector space addition, but that's not what we are thinking about. You're adding a two form to a two form to get you another two form, which is called a curvature two form, okay? And then we can learn how to write in general the curvature two form in terms of the vector derivatives of the vector potentials, and then the products of the vector potentials themselves. That's where the Riemann curvature tensor formula comes from, okay? So let's take a 5-minute break before we come back to patch up some of these holes in it, okay? So go back to basics and talk about differential forms. It seems that when you study differential geometry and the applications of differential geometry to physics, you need both tools. One of them is tensor analysis, the other one is differential forms. Relying exclusively on either one usually, produces some problems. It's when you know how to use both effectively, that's when the effective solution comes along, okay? Or at least the effective formulation of a problem. A good example is writing the curvature form as a differential form rather than as a tensor, okay? Then you can directly manipulate with those forms. So what is a differential form in general, okay? Again, I won't be able to go into all the details, but let me at least run through some of the steps leading to the concept of a general differential form. And I'm going to have to start off with the notion of the tangent space, and then the tangent bundle, and then the cotangent space, and then the cotangent bundle. And then imagining grouping together a bunch of those tangent and cotangent bundles to form a general tensor bundle, and so on, okay? Okay. So we have a manifold, okay? From the manifold, we can construct the tangent space or the tangent bundle. Tangent bundle. Well, let me consider a particular tangent space at a particular point x. In the manifold first. This is called the tangent space at the point x, okay? It's a vector space, okay? Then you can take the dual space of this, called a cotangent bundle, and we usually denote the cotangent, the dual object by a star. And so this is called the tangent space at the point x. This is called a cotangent space at the point x. X, of course, is a point in M. So, for example, if M is a sphere, then at this point, I can imagine a tangent space, which is a linear vector space like that. Okay? Now, this might seem a little bit of abstract, but it's directly definable in terms as the dual of this space. Anytime you have a vector space, you can define a dual space, right? So the notion of a dual space is very, very important. It's as a basic linear algebra concept. Okay. Now, then loosely, you can think of let me start from this side because it's in the development in this side which is more relevant for the definition of differential forms, okay? You can think of, let's say this is a cotangent space, right? I can also draw it like that because it's also a two-dimensional space, okay? It's not the tangent space, it's a cotangent space. It's the space which is due to the tangent space. Very abstract, but it's okay. All right. Pretty soon we'll write down specific objects in it. So you think of putting together all the different cotangent spaces, one at every point in the manifold. This becomes a, thank you, this becomes a cotangent bundle, okay? So I can think of the union over all the points in M of something like that, union over all the x's, okay? Now, there's a lot more details to be filled in, but very loosely you can think of this as the cotangent bundle, okay? That's a cotangent bundle. So then you can think of this whole thing as a differentiable manifold in its own right. Okay, you can think of the whole thing as a differentiable manifold in its own right. And so that a particular thing in here would be what? Like okay, before that I have to do one thing. Supposing I do something like this. I choose a particular vector in each of these spaces, like so. Now remember, those are the cotangent spaces. Okay, that means I have a vector field on the cotangent, a vector field on the cotangent bundle. Okay. No, I should say a vector field on M itself. But the vector quantities are vectors in the cotangent spaces, one at every point. Okay. And so then I can think of all the, I can think of tying a bunch of these together, tying together a bunch of these. Some finite number of them, okay? It's just a, at this point, it's just a direct product at this point. And so I can think of forming, this is called a vector in a cotangent bundle. It's actually a one form, okay? So to tie together this, it becomes, if there are R of these things together, it becomes an R form, okay? R form can be thought of as a vector in some higher dimensional space. And then you can think of anti-symmetrizing them. This is the critical step. You can think of anti-symmetrizing them. Anti-symmetrizing means what? Because you have R things in here, then it depends on the order of these things. An ordinary direct product depends on the order in each. But if you imagine taking a particular product and anti-symmetrize them, okay? For example, if you have something that is called T12, what does anti-symmetrizing mean? You add to that T21. Then you anti-symmetrize it, okay? And you can think of the same process of anti-symmetrizing a vector of any order, okay? And then, now after you've done the anti-symmetrizing of R of these things slapped together, so I'm going to introduce this notation. This thing is a result of anti-symmetrizing a direct product of R things. Each one is a cotangent space on M, like that. Kind of abstract, okay? And so this is called the form bundle of the Rth order, because it's built up of M star. M star means, well, I might as well say this is the, no, this is just a notation. The star, upper star means that I'm doing things on the cotangent spaces. This is not M star itself. This is T star, T upper star M at X, okay? It's just a notation, okay? Now I think of choosing a cross section. That means choosing some anti-symmetric vector at each point, okay? And then what I have is a field of forms now. I don't know whether I should. This gamma in here is the set of all cross sections, okay? And so this thing in here is the set of all cross-section. It's apparently a tensor field on the cotangent spaces, like so. And the mathematical notation that's being used is that this lambda always refers to antisymmetric objects, okay? And this gamma in here is like a vector field. It's called a cross-section. It's a space of all the cross-sections. So it's a space of all the vector fields, so to speak, okay? And so in this progression in here, coming back to starting with M, we have this. And then we have the bundle of exterior R forms. We bundle things together, lumping together all the cotangent spaces at all the x's. Bundle of exterior R forms. And then we obtain this thing that we have just written down. Okay. And oh, actually, this is not lambda. It's A. We call this A in here. So then we take the smooth sections. That means smooth fields. And I won't even explain explicitly what smooth means in this case on lambda rth order on a star. That is actually called the space of R forms. The space of R, A for antisymmetric now, okay? R forms. The space, so A super Rm is the space of all R forms on M. And now let me go back to the beginning and see how we can construct a basis here and then a basis here and then on to slap those together, anti-symmetrize them to form the R forms and so on and so forth. So let's start. We still have to, I think it's most convenient to think of some tangent vector first at a particular position x, okay? So when let me go back for a moment to this being the tangent vector. When I draw a vector at this point x in here that points in a certain direction and has a certain length, what can I use that vector for? Okay? Remember, it's a tangent, okay? So it must be a tangent to some curve that is on the base manifold. So a tangent vector at a point must be a tangent to some curve that passes through that point, okay? And if you take this curve to be small enough, that there's a unique correspondence in there, okay? Small segment corresponds. In fact, if you shrink it to exactly 0 length, the arc, then it becomes the tangent vector, so to speak. And so it tells you, one of the things it can do for you is to think of the tangent vector as some kind of a function that acts on a function on the base manifold. It tells how fast some function on the base manifold changes, okay? So for example, if you have a function x, which means a function on the base manifold where x refers to the set of coordinates on the base manifold, then you ask the question, how fast does that function change along the direction of the ith coordinate, let's say, okay? So that's the answer. And so we would write this as DIF. Okay? Write it as DIF. Now, if on the other hand, you think of the function f itself, basically DIF can be written as what? You can think of this other object in here, df, okay? df can be written as dif dxi, where I is summed over. Okay. And if you think of this as some small segment of a parameterized curve, okay, then every point along here can be represented by a set of functions like that, okay? T is the parameter in here, okay? Then you can actually think of finding the time rate of change of the function f when you move along this little curve like that, as time goes to 0, and that's the derivative, df dt. And so this is just like so, okay? And df dt is just xi dot, like so. Okay? And I think you can, let me just go ahead and try to write this slightly differently. You can write this as xi dot di, the whole thing operating on f like that. And look at this di as some, well, of course it is some differential operator acting on f like that, okay? But if you look at this object in here, right? Just by looking at the structure of the index positions, and the I is to be summed over, one up, one down, and so therefore it's like a scalar product, okay? Sorry, it's not a scalar product. It is like writing some vector v as viei, like so, okay? So that this guy can be thought of as the component of some vector along the ith direction, and this thing can be regarded as some basis vector along the ith direction. Rather abstract, okay? So a tangent vector, some vector, if it's a tangent vector, let me be explicit in here, can be written as x dot I times di. And this thing is then thought of as like a basis vector in here, okay? And these are the components. That's why in the classical mechanics class we said that the Lagrangian function is a function of the qi dots is a function on the cotangent space, okay? Function on the tangent space, rather. And yeah?
That di basis vector is
You can think of a particular tangent vector here as expressible in terms of some basis vectors. The first one is d1 and the second one is d2. It's pretty funny because the basis vector becomes an operator. It's an operator now. Okay.
Also a tangent of the ui curves, right? Like the ui curves from the
The tangent can be any you draw any vector, it's a tangent to some curve, right? It's a tangent to some curve. And so, so the basically, to specify tangent vector in here, you test how it acts on a particular function when the function changes along some curve in here, like so. Okay? And so in this sense, you can think of tangent vectors being written in this form where these are the components, and then these are the basis vectors like that. Okay? Now you can, this really depends on which curve you're talking about because that's a derivative of the parameterized curve. And that, of course, gives information on the direction. Once you've determined the curve, then you determine the tangent to the curve, then you determine the direction of the tangent vector. Okay? What I want to show you is that similarly, you can imagine here's the thing, df being acted on by di, and I'm going to use a quantum mechanical notation. One is a vector, one is a covector in this fashion in here, okay? And this is a funny notation, but I'm asking you to try to think of it a little abstractly in terms of the correspondence between the tangent space and the cotangent space. How can you write quantities in the tangent space, and how can you write quantities on the cotangent space? So up to this point, we know that we can write quantities in the tangent space by just giving some components I, whatever it is. These correspond to our xi dots, okay? di, where I is summed over. So it's just some general vector in the tangent space, okay? And I'm going to argue that I can write a general vector in the cotangent space by considering df as a general vector in the cotangent space, in the sense that something in the dual space acting on something in the original space produces a number for you. Because that's the definition of the duality of vector spaces. Okay? And now apparently we know that if we write df as equal to df df dxj dxj, this is a general df, okay? Well, these are numbers, okay, at a particular point. And so this is a tangent vi di. And if we impose the condition, this duality condition, that dxj acting on di is equal to delta ij, if we impose that condition, okay, then what we would have here is what? So this is some linear superposition of all the dx's. This is some linear superposition of all the differential operators in here, okay? And this would become df dxj times vi, and then multiplied by precisely this delta ji. But both I and j are to be summed over, okay? Let's say you sum over the j, then this immediately produces df dxi vi, like so, which is a number, okay? So in this sense, the df can be considered as a vector in the cotangent space, and then this guy can be considered as a vector in the vector space. And since cotangent and tangent spaces are dual spaces of each other, you can think of any object in each one of those as being a function on the other one. Okay? That's how dual spaces are defined. So we have what is called the natural frame field. In both the tangent spaces and the cotangent spaces. The natural frame field in the tangent space would be all the di's. I goes from 1 to the number of coordinates. And the frame field, natural frame field in the cotangent space would be the set of all the dxi's. Okay? And as soon as we have this duality relationship, which is that delta I acting on dxj is equal to delta ij, Kronecker delta, then we've got the complete duality relationship established. Okay? So, and that's the whole basis. Now let me show you why it is that I have written one of these guys as a subscripted guy and the other guy as they have to be written that way as a superscript, because I can now show that they transform inversely to each other. Okay, so let's see how dxi changes under a general coordinate transformation, and then let's see how delta I changes under general coordinate transformation. Okay. So let me consider a coordinate transformation going from xi to x prime I. In other words, each of the x prime i's is a function of all the xi's. All right? So, or conversely, each of the xi's has to be invertible. Each of the xi's is a function of all the x prime i's and so on and so forth. Okay? So how would I write dxi? Dxi would then be simply equal to what? You consider each of the xi's as a function of all the x primes, so it would be dxi dx prime j dx prime j, but the j is summed over. Okay? When you consider this guy, you see there's a whole bunch of those, right? It forms a matrix because two indices in here. Okay? What is this matrix called? It's called a Jacobian matrix. Okay? You can calculus transformations of variables. It's called a Jacobian matrix. Okay? So you can write, for example, if you look at this, define this thing to be aij. Right? So then you have dxi is aij dx prime j, and the transformation matrix is this guy in here, like so. Okay? When evaluated at a particular point in the base manifold, these are constants in here. Okay? So you have a linear transformation like that. Okay? At each point x. Okay? Now let's take a look at how this guy transforms. To see how this guy transforms, I think it's convenient to imagine that to go back to its original duty, and that is it's used to differentiate some function. Okay? So let's calculate this derivative. Okay? But I'm going to calculate it through the chain rule. Okay? I first imagine, now the function f is originally given as functions of the xi's, but now I imagine all the xi's, each of the xi's to be function of all the x prime i's, so that implicitly this is a function of all the x primes also. Okay? Once I'm given this transformation in here. Right? And so how do I do that derivative? I do that by chain rule, which is dj, let me write it explicitly, df dx prime j dx prime j dx I. Is that okay? Summed over j. All right? This is just a chain rule in partial differentiation. Okay? And so I can write this, switch these two factors around. I write this as dx prime j dxi df dj. But now I'm going to adopt the notation called as d prime j. Okay? Prime means it's differentiation with respect to the primed coordinate. So d prime j f. Okay? Now I simply strip away the f, right? So that I can now write di is equal to dx prime j dxi d prime j. Okay? Now, this can also be thought of as a matrix because it's got ij on it. But what's its relationship to the original matrix? The original matrix has got the unprimed variables on top. The new matrix has got the primed variables on top. Huh? Transpose or inverse. Inverse matrix, the inverse Jacobian matrix. The second one is the inverse. This is A inverse. If this is A in here, if this is Aij, okay, this is the inverse. This is the Jith element of the inverse, like so. Okay? And so now you have the other transformation, which is that di, I'm just writing as A minus I by J D prime J. Okay. Now you compare the two transformations. Obviously, one transforms as the inverse of the other one. Okay. So hence, if one belongs to a certain vector space, then the other belongs to the dual space. Lower index objects and upper index objects transform inversely to each other. We go back again to your chapter 1 in your classical mechanics text. Okay? That's why we have to make the difference between covariant objects and contravariant objects, because they transform inversely with each other. Okay? So now I've got this picture, right? If I limit myself to the cotangent side of things, then I have these objects which are linear superpositions of the dxi's, these objects, and those are the cotangent vectors. And those are the one forms. Okay? Because after all, what is a linear superposition of? So if I write a form like this, forget about all that. Now we get to the simpler stuff. Once having established this, to some extent, now I can write a one form as f1 x dx1 plus f2 x. X here means shorthand for all the coordinates, okay? dx2 up to fn x dxn, so on. Okay? That's something that lives on the cotangent space. That's something that lives on the cotangent space, okay? So one form, if you have n coordinates, one form involves knowledge of n functions on the manifold, like that. Okay, this is called differential one form. And it's already anti-symmetric, so to speak, because there's nothing to anti-symmetrize. Okay, there's only one object, okay? So it is its own anti-symmetrized version. Now, you consider multiplying these two things together as direct products, right? So if I come in with another one form, which I'm going to call something different, what do you want to call it? Omega, let's call it theta. No, one form also, okay? And so you write this as G1 x dx1 plus G2 x dx2 plus. Now, doing this is only doing it locally, okay? Now, this is a very important point which tends to get swarmed up because, you know, I am already working with a specific set of coordinates, okay? And so, in general, in a differentiable manifold, a specific set of coordinates is only applicable within a certain region, a neighborhood in a manifold. As you can see, once you go to S2, you can't use the same set of two coordinates, theta and phi, for every point in the manifold. You have to at least have to have two regions, okay? Two charts, so to speak, which together form what they call an atlas, okay? So you look at the atlas of the globe, you need at least 2 pages. You can't project everything onto one flat page. You can't project the entire two-dimensional sphere into one flat space. You have to chop it up into various pieces as we do in an atlas, okay? And then do a projection. So different pages of the atlas are called different charts, and then the different charts together are called the atlas. So in a differentiable manifold, usually you have this situation like that, where you put together different regions. In each different region usually requires one particular set of coordinates. Then the important thing is what happens in the intersection between two different regions. So here you have one set of coordinates, here you have another set of coordinates. For the whole thing to be called smooth, the mathematical requirement is that the coordinates within the intersection region, the coordinates in one chart must be expressible as differentiable functions of all the coordinates of the other chart. If you have specified all those rules for piecing together all the different charts, then you are said to have specified a particular differentiable structure for a particular manifold. Okay? So when we write expressions like this using a particular set of coordinates in here, it is important to keep at the back of our minds that these expressions are necessarily local expressions because I'm only using one set of coordinates. Okay? Be that as it may, we're going to continue writing in this fashion because in physics applications, a lot of times you really don't have to worry about the explicit differentiable structure of the particular manifold. Sometimes you have to, but many times when you do straightforward calculations, you don't have to. So let's just write the differential forms like this, okay? So now, when you slap these two together, what do you get? When you slap these two things together, you get a direct product. But when you write a direct product, you have, now these functions are just considered as scalars, so you can put them anywhere you want, okay? But it's these things, the positions of these things are important, okay? So you may have things like dx1 first and dx2 second, okay? Or dx2 first and dx1 second, and so on and so forth. When you put the whole things together, then 1, 2, 3 times 3 is 9 terms, okay? So they would have things like 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Okay, there's no particular symmetry structure to this. Now then the next step is called anti-symmetrizing. You anti-symmetrize the whole thing so that the whole thing becomes anti-symmetric with respect to interchanges of these differentials in here. When you do that, then you're said to have made a differential form. In this case, a differential 2 form in here. And the slapping together is then written using the so-called wedge. That's called an exterior product, okay? Now, when you anti-symmetrize, apparently all you have to do is to, when you anti-symmetrize, you don't have these, right? You don't have these anymore, okay? But you have these, but this is the negative of this and so on. This is the negative of, we have seen it many times. This is negative of this and so on and so forth, okay? After you've done the anti-symmetrization. And so I write the whole thing as summation over ij dxi wedge dxj, and then simply with something that has the two index like that, okay? Let me just call that fij like that, okay? And I really, you know, I can, if I put the unrestricted sum in here, I would, disregarding this, I would still have all the 6, all the 1, 2, 3, 4, 5, 6, but there are only 3 that are linearly independent, right? Because this is negative that and so on. So sometimes I can write it like this. I impose the condition that I is equal to j, and then that would be a general form, right? If I don't impose this condition, I would be redundant. It would be redundant because dx1 wedge dx2, because it's anti-symmetrized, is equal to minus of dx2 wedge dx1. So this wedge product in here automatically takes care of all the anti-symmetrized properties for you. So it's very convenient to use, okay? Remembering this rule in here, a couple of rules of exterior products, then you can do all sorts of slapping together and then anti-symmetrize. After the anti-symmetrizing step, then you are said to have formed a differential form, which is short for exterior form. And exterior form is always anti-symmetrized. And we sometimes skip the word exterior and just say differential form, okay? Like that. So we have a 1 form, we have a 2 form. Similarly, we can think of a 3 form. And the 3 form would be something like dxi, dxj, dxk with something in here which has the 3 indices ijk and so on and so forth. So summing up just all the independent elements, okay? So in the case of 3 dimensions, these are the only 3 independent elements. So this would be dx1 wedge dx2 This would be dx1 wedge dx3, and this would be dx2 wedge dx3. And a general 2 form then can be written as a linear superposition of these three things. This satisfies, whoops, I just erased that I is less than j, because in all of these I is less than j. 1 is less than 2, 2 is less than 3, 1 is less than 3, and so on. Okay? So for higher order terms, you just have to write all the terms for just fish out all the linearly independent ones. Okay? In other words, imposing some restriction on the ij case and so on and so forth. Okay. So then I have built the differential forms. And remember that for a manifold of dimension n, the top form is an nth order form. Okay? Because whenever you try to introduce an n plus 1 form, then you have some repetitions among these x's. And once you have the repetition, because of the anti-symmetry, it gets killed. Okay? So that's differential forms. Okay? Now we consider exterior derivatives of differential forms. And the general rule is this. And after that, I think it's about time to go. Maybe give me 5 more minutes. Still written in terms of local coordinates. Supposing I come in with an R form. Okay? And an R form is written in general as, suppose that omega is an R form. And I'm going to write this as, an R form has got dxi1 wedge dxir. There has to be R of these x's, okay? And I got to have a coefficient in here, ai1, ir, okay? And then you have R sums in here, sum over I1, sum over I2, and so on and so forth, okay? Okay. Actually, you can write this as an unrestricted sum, okay? And then you can combine them. It's the same thing, okay? Now then, if this is a given R form, what is then the exterior derivative of this given R form? And notice very carefully how you compute it, okay? Now this guy in general is a function of all the x's, right? So I'm going to partially differentiate this guy, ai1, ir, with respect to some xj, and then sum over the j by attaching a dxj here. And then this stands before all the things that are already there. It has to stand before. This is a rule. And this rule can be proven. I'm not going to prove it. Okay, based on some general procedures for exterior differentiation. So once you've done this, then you've got an R plus 1 form, right? Because there are R plus 1, these indices now. There are plus 1 sums in here, sum over j, sum over I1 through sum over IR. Okay? So you have an R plus 1 form. And this is really the only rule that is most important for you in the sense of using it for computations. Okay? So from now on, when you're asked to differentiate a one form, you use this formula in here. Sorry, when you're asked to differentiate a general R form, you use form. R can be anything. Okay? Now, out of this rule in here, you can immediately prove 2 very important rules. The first one is called a product rule of exterior differentiation. And the second one is the fact that d squared is always equal to 0. Let me write the second one first. Both of these can be proven from this formula, so to speak, for the calculation of exterior derivatives. So supposing that I have R omega s, I calculate the derivative, the exterior derivative of the wedge product. The wedge product is defined so that when you have an R form, when you have an S form, you anti-symmetrize them after direct multiplication. Then the whole thing is again anti-symmetrized by definition. Okay, so Now this is obviously some kind of a product in here, the product being the exterior product. And then you would be tempted to say, oh, okay, there must be some kind of Leibniz rule corresponding to the product rule for ordinary differentiation. So indeed there is, okay? The rule is this. You differentiate the first one first, use it to wedge with the second one, and then there's something in here, and then you have the first one wedge with the derivative of the second one. This is a product rule. In ordinary differentiation, that would be it. But here, you have to add a factor. -1 raised to the order of the first one. The second one doesn't count. Doesn't matter what S is, okay? This is the rule for the so-called product rule for exterior differentiation. Next time we come back, actually you can look at it after I send you the solutions, because both of these proofs are one of the problems in the chapter 41 in the quantum mechanics excerpts, and all the solutions I'm going to give to you, okay? But we'll go through this next time when we come back. Oh, next time will be Monday. We still can go through this before the midterm, okay? So that's it, you know, to understand how to do exterior derivatives. That's it. That's all you really need to know, okay? From this, you can prove that the derivative, the exterior derivative of a one form corresponds to taking the curl of a vector, and the exterior derivative of the two form corresponds to taking what is it? The del dot, okay? The del dot.